Hello and welcome to another video of integration techniques. We are doing substitutions, and in particular we're doing perfect substitutions. And the reason I'm calling it perfect is because whenever I do the substitution, the du will appear exactly inside the integral. Now we have seen a couple of examples the last two videos. We talked about perfect substitution. So this is the last example I'm going to give you about a perfect substitution. We'll also do another substitutions which won't be perfect but still be substitution. So let's look at this integral. It's going to be the integral of this fraction e to the x minus e to the negative x divided by e to the x plus e to the negative x. At first glance it looks like it's going to be a very difficult integral, and the key part here in all this substitution is getting the value of u. What is the expression of u that's going to make our integral easier? So that's the purpose of the substitution, to make things easier. Now remember the steps is that you're going to choose u, that's an expression inside the integral, and it's usually under square root, denominator, or something like that, argument of a function. Now what I'm going to do here is I'm going to try the denominator of this fraction here, and you will see in a second why. So let me choose u to be the denominator, so it's going to be e to the x plus e to the negative x. And actually what I'm doing here is I'm choosing just the denominator of this expression here, the one that I'm coloring here in yellow. Now the reason I'm doing that is because if you look at this, if I call this u, the du will be the top. Now, it will be a good idea that you are quick and good with the rules of differentiation, because it will actually help you to choose what u is. So if you know the rules of differentiation, will be a lot easier for you, because if you know exactly what the derivative is, you can actually search for it here in the integral. So I'm going to try this u here, so it's e to the x plus e to the negative x. Now, after you choose your u, remember the next thing you have to do is compute the derivative of that. So I'm going to do in the second part, which is, I wrote it down here again, you compute the du, which is the derivative of the expression in terms of x, if the variable is x, or no other variable, if it is a variable t, w, s, whatever the variable is. And you simplify the expression, and that expression du should be inside your integral. Now, if you look at what I have here on my screen now, if I take the derivative, which is I'm going to compute du, the derivative of e to the x is of course e to the x again. I'm going to put that in parentheses because I'm going to add the dx at the end. And the derivative of e to the negative x is negative e to the negative x, and I multiply by dx. Now the reason that is like that is because there is a rule, remember. I'm going to put that rule here. The rule of a differentiation, when you have a constant a that is non-zero, the derivative of that prime there means derivative, is the constant times e to the ax. That's exactly the rule that I use here that was coming from this part over there. So in this case, my a is -1, if you want. So that is the du. Now, if you look at this expression that is here, is e to the x minus e to the negative x dx. This expression is exactly the numerator of my fraction. So that is why it's a good choice to make u the denominator. So now once I have that, so the du is exactly something that is in my integral, now I'm going to make the substitution. I'm going to write down the integral again so you can see how the substitution is. So my original integral is e to the x minus e to the negative x divided by e to the x plus e to the negative x dx. And I'm going to rewrite it like this so you can see exactly what the substitution is going to be. So I'm going to say 1 over e to the x plus e to the negative x. I'm just splitting up that fraction times the top, which is e to the x minus e to the negative x. I'm going to put the negative x there, negative x, and that's the dx. Now, the reason I wrote it down like that is because it's going to be easier for you to see what the substitution will be like. Now, this expression that is here is exactly the same as this expression that you see over here. They're exactly the same when you multiply these two expressions. Now, if I write it down like that, what happens is, remember that this guy here that is in the denominator here, this is going to be u. And this whole expression that is here e to the x minus e to the negative x dx. That's going to be just my du. And as you can see now, we can make the substitution. So if I write it down here, this is going to be the integral of 1 over u du. Now my integral is completely in terms of the variable u, and that is important to have. As you can see here, it should the new integral should be in terms of u, and also it should be easier. So the purpose of the substitution is to make things easier. So in this case, of course, this integral that is here is a lot easier than the one that is right here. And if you remember the rules of integration, this is the basic rules of integration. This is equal to the natural log of the absolute value of u plus c, plus the constant of integration. Never forget to add that c there. It's very common to forget that c. And why is this one like this? Is remember, that's the basic rule. So you should know these basic rules to be able to apply the integration techniques. Now, of course, you cannot leave the answer like this because the question itself was in terms of the variable x. So I have to go back and replace what u was. Now u, if you can see here, u is this expression that I have here, e to the x plus e to the negative x. So I just, to write just my answer, this will only be ln of e to the x plus e to the negative x, and then just plus c. And this expression that I just wrote down over here, this one, ln of this absolute value here, will be my answer. In reality, I don't need the absolute value here. You will need it if this expression were, for example, sometimes negative, but this expression that is here is always positive because the exponential to any exponent, whatever this exponent is here, it doesn't matter what it is, it's always a positive number. So I can actually get rid of that and just write down this is ln of just e to the x plus e to the negative x plus c. So I don't need the absolute value in this particular case. So this is an integral that looked a little bit scary at the beginning. It was not that bad with that substitution. So this is the last example of a perfect substitution in the sense that when I choose my u, the du is exactly there. So this is u and the du is exactly there. Now let's do one then that is not necessarily a perfect substitution. You're going to be off by a constant. So I'm going to call this example off by a constant. And what that means is the du is not going to be exactly in the integral, but it's going to be off by some constant. And that will be okay. Now let's look at this integral here. So I have the x to the 6th power times the sine of x to the 7 dx. Now, the first thing we do always, because we are using a substitution, then as you remember, you have to choose u, that is an expression inside the integral. Remember, it's usually an expression under the square root, the root, denominator, or the argument of a function. Now, if you look at this expression that is here, I don't have denominator, I have a square root. The only thing I have is argument of a function, which is the function itself here, the sine. So let's try, for example, this guy here. Let's try u equals to x to the 7. So let's try that one. So I'm going to try my u equals to x to the 7 power that I have here. Now remember that the integral is x to the 6 sine of x to the 7th power dx. So I'm naming my u to be the argument of this function sine that is here. That's only the first step. So u should be something inside the integral. The next step, remember, is I need to compute the derivative of that, which will be my du. So let me do that in here. So the du here, the derivative of x to the 7, this is just the power rule for differentiation. So I'm going to apply the power rule here. So that will be 7 x to the 6 dx. Now, you can see here that I don't have 7x to the 6 dx. If you look at the integral that I have over here, I have x to the 6 dx, which is here. X to the 6 dx, I have it. But I don't have 7. This is what I mean off by a constant. You don't have the du exactly in the integral. You're just off by a constant. But we can fix this very easily. If you are off by a constant, the only thing that you have to do in this particular case is you will only have to divide. So for the next step, what I'm going to do is I'm going to divide by whatever the constant you are off. So I'm off by this constant 7, which I don't have it here. So I'm going to divide by that constant 7 on both sides. So if I do that, then I will get the following expression. I will have du divided by 7 that is equal to x to the 6 dx. So the only thing I did there was just divide by 7 on both sides. Now this expression that I have here on the right, x to the 6 dx, appears exactly in my integral. This is x to the 6 dx appears exactly in that integral over there. Now with this in mind, let's keep this in mind because that's important. So with this is here, this whole thing that is here will be important. Now what I can do is I can go ahead and then make that substitution. So let me write down the original integral again. So the original integral was the integral of x to the 6 sine of x to the 7 dx. What I'm going to do is I'm going to bring this x to the 6 and the dx together so you can see the substitution. I'm just going to move things around because it's multiplication. I can do that. So this is x sine of x to the 7 times x to the 6 dx. So the two terms are exactly the same thing. I didn't do much here, just commutative of the product. Now let's do the substitution now. So if we do the substitution now, remember that this guy x to the 7, that's what I'm calling u. And this guy here, x to the 6 dx, that's not du, but if you go back here, x to the 6 dx is du divided by 7. So that expression that you see there, this guy over here is, let me write it down, this is du divided by 7. So if I make my substitution here, you will see that I will get this. So I'm going to get the integral of sine of u times du divided by 7. And that's fine because then I can say the following thing now. This 7 is a constant. What I can do is I can pull it out of the integral. So then I can say this is exactly the same as 1/7. Now remember that 7 is in the denominator. This is integral of sine of u du. I actually don't need a parenthesis there because this is not an expression with several terms. It's just one term. This is the variable u. But I'm going to keep it there for a second. As you can see here, the purpose of the substitution is to make the integral easier. So this integral at the beginning was not, it's not complicated, but it's, of course, this one here is a lot easier than that one. So now I can actually apply some of the basic rules of integration. So this is going to give me 1/7. Oops, let me write down that better. This is 1/7. And the integral of sine is negative cosine. So this is going to give me negative cosine of u. And I'm not going to use the parentheses anymore. And remember to always add the constant of integration. So this is going to give me negative 1/7 of the cosine of u plus c. Now remember that this is not the last answer because what I have to do is I have to replace back what this u was. Now let me scroll up here and say what this x to the 7 is exactly u. So that's what I have to replace back. So then this guy over here, the final answer for this particular problem will be negative 1/7 of cosine of x to the 7th plus c. So this will be the answer. If you actually take the derivative of this expression here, the derivative of negative 1/7 of cosine of x to the 7th power plus c, this derivative will give you exactly x to the 6th sine of x to the 7th. You should try it out and see that actually happens. Now, this example was one of some that I'm going to do that you're going to be off by a constant. Now, remember, off by a constant, let me scroll up again here, is that the du is not exactly inside the integral, but it's just off by some number. So that's the second example of off by a constant. The next video will talk about another two examples where you're gonna also be off by a constant. So I'll stop the video now and I will see you in the next video. Thanks for watching.